In this problem, we're going to be looking at induction. Specifically, we are going to be looking at how to solve this specific problem for induction. However, we are going to go over the 4 steps that you can use to solve for any mathematical induction problem whatsoever. So the first thing that you're going to want to do is test the base case. This is usually the lowest and most simplified case that we can use. So for this, normally, if we didn't have a boundary, we would start with, say, 0. However, this is for if n is greater than 1. Since n has to be greater than 1, we're going to test for 2. So we're going to say that n is equal to 2. And now we're going to plug this in for all of our n's. We are going to have 2 squared, and this has to be greater than our 2 factorial. Now we can multiply this out. 2 squared is going to be 4, and 2 factorial is just 2 times 1, so this will give us 2. We can see that this holds true, and our base case has been tested. Now, we need to assume something, and usually mathematics you don't want to assume, but for this you need to. So to assume, we're just going to do some light assumptions. Basically, we're first going to start off by saying that our n is equal to k. We're just substituting, so that's okay. This is going to give us k to the kth power, and this has to be greater than our k factorial. So this is going to be the equation that we're going to look at. After we make this assumption, we can start proving our induction. So we previously found this in our base case. Now we want to solve for one more than this. So we're going to solve for k plus 1. That means wherever we have a k, we're just going to plug in k plus 1. Plugging this in, we are going to have k plus 1 raised to the k plus 1 power, and this has to be greater than our k plus 1, and this is our factorial. Now we want to write this out in simpler terms. So to do that, what we're going to do is simplify this. Using the rules of exponents, we can have our k plus 1 separated. So we're going to have a k plus 1 to the kth power, and then we are going to have it being multiplied by k plus 1 to the first power. And this still has to be greater than our k plus 1. However, using the rules of factorials, we know that this k plus 1 factorial is basically k plus 1 times k minus 1 times k minus 2 times k minus 3, and so on and so forth. But we can rewrite all of that other stuff as just k factorial. So we're going to have k plus 1, this is in parentheses, times our k factorial. That is going to be our new equation. Now, how would we solve this? Well, if we look back at step 2, we can see if we multiply both of these by k plus 1, which we can do, because remember, if we do something to one side, as long as we do to the other side, it's completely legal. So after we do this, we're going to see that we get a similar form. We're going to get k plus 1, and this is still k to the exponent, and then this has to be greater than our k plus 1. This is being multiplied by our k factorial. Now this looks very similar to this. In fact, it's the exact same thing. And we know that this part has to be greater than this part, because all we're doing for this part is just finding what our second part was, but plus 1. So 1 more than our second part. And if we're finding 1 more than the second part, we know that it's greater. So this number 2 is basically in the middle of this right here. And if it's in the middle, that means it has to be less than our max, but greater than our minimum. So if we rewrite this, we are going to have k plus 1 to the kth power. We're going to have k plus 1, this is the first power, and this has to be greater than our k plus 1 multiplied by our k to the exponent of k. And this has to be greater than our k plus 1 times our k factorial. And if we look at all of this, it's basically the same exact thing as what we have right here. So we can rewrite this as k plus 1, and this is the exponent k plus 1 after we combine these both together. And this has to be greater than our k plus 1 factorial. Again, if we write this back together, therefore, it has been proven. Now, we just need to explain our results. Our results are basically just going to state that if our statement is true for n is equal to k, which we assume right here, then it is also true for our k plus 1, which we showed right here, and then further proved over here. So that's how you would go about solving with mathematical induction.